Yeah, thank you, and thanks for having me. I'm sorry we can't all be together in person. I was really looking forward to spending Sandia's money traveling to Vienna, and now sadly that won't happen. But we've heard a lot of talks in the last couple of days about activity, and activity is certainly a fascinating way that we can drive systems out of equilibrium. Today, I'm not going to be talking about activity. I work in the study of the deformation and flow of very viscoelastic and nonlinear materials. And what I hope to share with you today is that, one, we can model them and find many interesting physical phenomena in them, but also that they're also a very powerful and poorly understood area of physics for both in industry, but also in biology. So while it's true that many animals in nature use activity to drive various physical behaviors, they also use traditional nonlinear out of equilibrium flow to produce fascinating and interesting phenomena. So my favorite is the orb weaver spiders. I spent most of my PhD studying fiber spinning, and in fiber spinning, just like what this spider is doing, you take a polymer solution, you rapidly deform it, dramatically increasing its surface area to volume ratio. And this increase in surface area allows solvent to evaporate very rapidly, which induces crystallization of the polymer chains, which have been distorted very far from equilibrium, and produces these very interesting and robust polymer fibers at room temperature, being deformed at rates that a spider can do by hand with no toxic ingredients. And so this spider has mastered the art of harnessing the non-equilibrium physics of nonlinear flows to produce an interesting and useful structural material. And much of my work and interest is understanding how they do that and how we can apply those kinds of ideas in our own creation of polymer materials. So I've put a variety of polymer materials here. What I think is most interesting about polymer materials is that they are cheap, they are light, they can be processed near ambient conditions, but also polymers are highly orientable. It's very easy to deform them at speeds that cause the underlying molecules to orient and elongate in the flow. And you can use that to your advantage in processes where you dynamically change the flow, like 3D printing, to tailor not just the geometry of your materials, but also their material properties in specific locations, whether those be mechanical or optical properties. The challenge is when you talk about manipulating the microstructure of polymeric materials, you have to face the two very challenging aspects of polymers that arise, and that is that polymers are long and extended objects. They are, most of us probably know that they're formed out of many repeating units connected into different kinds of continuous chain-like architectures, whether that be linear chains, rings, or stars. Another important feature of polymers is that they intermingle and entangle with one another. I'm going to be talking to you about polymer melts, and in polymer melts, you have a dense collection of chains that intermingle, interdigitate, and entangle, and they produce emergent structures of entanglement that dominate how they respond to external applications of deformation and stress. So how individual chains respond to a flow or deformation is transmitted to them by this mesoscale superstructure of entangled objects. And that produces a very rich and complex dynamics that we have to figure out how to study. But at the very base, we're interested in two things. There are going to be polymers that have some characteristic dynamics and relaxation times, and there's going to be us imposing some kind of external flow with its own time scale. And these time scales will compete. So for instance, I'm going to talk to you today a lot about uniaxial extensional flows. That's what the spider was doing, where you stretch a material along one axis and it contracts in the other two directions to maintain volume. And if we deform the material slowly enough that the chains can diffuse, there will be no effect on the chain structure. The chain conformations will stay largely the same. And the properties of the fluid and the properties of the solid, if you allow it to cool down and solidify, will be unchanged from before the flow. But if you deform fast enough, then that flow will induce possibly quite dramatic elongation of the polymers, which can be frozen into the material after processing. Or even during processing, it'll produce dramatic changes in the flow behavior. So this is most often seen as these very exotic nonlinear viscoelastic phenomenon. So we saw a talk earlier that was talking about shear thickening of colloidal suspensions, but also you can get exotic physics due to normal stresses building up. So if you imagine wrapping pasta around a fork, polymers are like long molecular noodles. They can also produce normal stresses that cause them to climb up rotating objects. And so you get these kind of exotic rod climbing behaviors, which are interesting, but very annoying in an industrial context. This is a very good way to break down a practical processing machine. Or if you're a baker and you've ever tried to use a KitchenAid mixer to create dough, you constantly have to shove the dough down because it wants to climb up out of your KitchenAid or wants to gum up your rotor. So it's a thing we need to know how to control. So the way we probe these kind of nonlinear phenomena, particularly extensional flows, is we do what's called filament stretching rheometry. So you take a filament and you stretch it exponentially in time, because a constant extensional strain rate is exponentially elongating your sample in time. So it very rapidly becomes very skinny. And then you can see this little glowing green right here. This glowing green is two crossed lasers, because what happens is you measure the diameter of the center of the filament actively, and you use that in a feedback control to control how rapidly you elongate to make sure that the diameter is shrinking at a constant strain rate. Because this is a fluid filament, and there are instabilities, there are issues of non-uniformity, and so you have to work very hard to keep it at a constant strain rate. But if you do that, then what you can measure is something like this. This is a transient viscosity curve, and it measures the evolution of the extensional viscosity of the fluid over time. And the first thing I want you to see is that the viscosity changes by orders and orders of magnitude over decades in time. A very large hierarchy of modes contributing to the viscoelasticity of this polymer. And if you deform the fluid in a weak linear limit, you'll get the same curve every single time you stretch the material. However, if you go to a strong flow where we are presumably distorting the material out of equilibrium, then what you'll see is a nonlinear viscosity curve that looks something like this. At short time scales, where the modes are fast enough that they're still in equilibrium, you will fall on the equilibrium linear response curve. But once you get to time scales where your strain rate has driven you out of equilibrium, you start to deviate. Those modes are driven out of equilibrium, and that's evidenced in the experiment by this nonlinear plateau that's not necessarily the same as the Newtonian viscosity. And it gives you some new viscosity that is somehow fingerprinting the change in conformations of the material that you have imposed with the flow. And a lot of what we want to do is understand how these macroscopic processing relevant changes in the nonlinear behavior are caused by molecular scale processes. So I mentioned earlier that polymers and how you transmit deformation from the macroscopic scale down to the molecular scale is mediated by these mesoscale structures, this due to the entanglement of the chains. That's relevant for a couple of reasons. So I just want to point out the idea is that for any chemistry, if you connect it into long chains and put a lot of those long chains together, at large scales, the functional form of its behavior is going to develop a kind of universality that is not dictated by the details of this monomer, but is dictated by the topology and geometry of putting a bunch of long strings in a box together and allowing them to thermally diffuse. The structure of this entanglement network is more relevant than the fact that these strings are made up of monomers of a specific chemistry. The chemistry comes into play in certain unitful quantities that scale the behavior. But at the end of the day, when you talk about, for instance, linear chains, all you care about is how many entanglements each chain forms, which is a dimensionless quantity. And so you get this emergent material parameter that we call the entanglement segment length, which is how many monomers it takes to form an entanglement in the melt. And then you can talk about the molecular weight of your chains in terms of how many entanglements each chain forms. This is relevant to what I'm going to talk to you about, because the fact that there's this sort of universal description that's chemically agnostic means we can use very simple simulations to reproduce experiments on specific chemistries, which is going to turn out to be really useful. I'm going to skip over this a little bit, but the idea is you can study the properties of this entanglement network and understand how entanglements cause chains to diffuse sublinearly, and use that to understand the hierarchy of relaxation modes. So this is talking about the tube model of entangled polymers, and I don't really want to unpack it all, but the idea is that entanglements confine chains and force them to diffuse upon a very limited number of directions to go around each other. And that produces this large hierarchy that we saw in a linear response curve that led to this massive increase in viscosity over 8 decades in time or so. The point is that everything about this spectrum can be derived from, you see this Z, this is the number of entanglements per chain showing up. The spacing of the modes in the spectrum is entirely determined by how entangled each chain is. So there's a fundamental time scale called the entanglement time. That's a chemically specific quantity. And there's a fundamental length scale, which is the number of monomers per entanglement. That's chemically specific. But once you have that fundamental time scale, and once you have that fundamental chain length scale, everything else is derived in terms of them. And so if you can create a model that has a similar ratios of these quantities, then you can reproduce the experimental behavior. So now when we impose flow, the idea of flow, right, is it's going to compete with these length scales. So for instance, for the linear polymer chain, there's a time scale on which the chains reorient, and there's a time scale on which chains stretch. So if I make my strain rate faster than the time scale on which the chains can reorient, can rejuvenate their tubes, if you're familiar with tube model words, then my flow will cause the chains to orient. And if I go faster than the time scale on which chains stretch, then I can start to stretch out the chain. I won't just reorient it in its entanglement network. I will actually start to unravel the entanglements themselves and make chains stretch out. So when we talk about flows in polymers, it's especially important to use a Weisenberg number, because you need to talk about which set of modes you're comparing the flow strength to. And so in this talk, what we're going to use is what's called the Rouse-Weisenberg number. We're interested not just in these objects orienting, because, you know, we want to, on the left, you have the chain trapped inside of an entanglement network. On the right, you have a chain trapped inside an entanglement network. It's just elongated. We're interested in destroying that entanglement network. We want to know what happens when you dramatically stretch out chains and they begin to stretch so much that you don't even know if you can apply equilibrium ideas to describe what they're doing. So here's sort of a motivation for doing this, and then we'll just jump into some data relatively quickly. Is on the left, I'm showing you 2 different polymer melts, and they have identical linear viscoelasticities. So their black curves are identical, which means they have the same equilibrium theory. However, if I go to stronger and stronger flows, you'll see the plateaus in their nonlinear response follow different rate dependencies. So equilibrium physics is insufficient to explain what's going on out of equilibrium. And that's where we want to come in with simulations. we're missing physics, or new physics is coming into existence or emerging in the flow. The problem is when you do an extensional flow, this is your sample, and it very, very rapidly breaks up due to capillary instabilities, or even if you manage to freeze this, like take the sample to right here, cool it below TG, and then collect a dozen samples so that you can put them in a neutron scattering experiment, but then you have to deuterate some of your sample to, it's a very difficult system to characterize microscopically. So what we do is we do molecular simulations with a relatively simple bead spring model, and we're going to deform them in extensional flow. And we're going to try and understand what the rheology is and how it's related to the microstructure. Now, what I've been emphasizing a lot earlier is important because the fact that we can have this generic physics mean the fact that we have this sort of generic, universal, mesoscale dominated object that controls how we experience externally applied deformations. The hope is that in non-equilibrium environments, we can also, if we match these generic properties, like how long entanglement segments are and how many entanglements there are per chain, we can also reproduce nonlinear physics. And it turns out that that's true. The one caveat is the one extra ingredient we need is we need a better way to do extensional flows, because just like experiments, the simulations suffer from this exponential contraction of the sample as time goes by. This took me a year to run, and it's rapidly failing. And so very recently, I've been applying some new boundary conditions that were recently derived by some clever applied mathematicians that look a little wonky, but what I can tell you is that this system is doing exactly what this system is doing, but we're leveraging the freedom given to us by working in 3D periodic spaces to prevent the system from ever getting too skinny to do uniaxial flows. And the kicker is that this system is this large compared to this system, which means we can go to indefinitely large strains with a much smaller system. And that allows us to directly reproduce experiments. So I'm just going to skip the details. I'll talk to you about them offline if you'd like. But this is what you can get. So on the top, I'm showing you experimental data for a well-entangled polystyrene melt. This polystyrene has about 20 entanglements per chain. And on the bottom, I'm showing you bead spring simulations for a system with matched entanglement networks properties. So the number of monomers per entanglement and the number of entanglements per chain and the Weisenberg numbers of the flows have been matched. So we can directly compare the bead spring molecular dynamics simulation to the macroscopic rheology experiment. And we can reproduce, we can get to Newtonian response, we can get to strongly nonlinear response. And we can reproduce the rate dependence of the polystyrene with spheres. And so this is just to convey to you that all that the styrene unit did in this system was provide a time scale for friction. And you know, our system has a slightly different time scale, and that's absorbed in the Weisenberg number. So we can reproduce the nonlinear physics. So now let me show you a really neat system. So we can reproduce linear rheology of linear chains. So let's go have some fun with something more complicated. So I have some colleagues, Dimitris Vlasopoulos and Shane Huang came to me and they said, look at this data. And so what they have is, this is a linear polystyrene, and it's doing what we just saw. As you increase the rate, the viscosity goes down. Here is a ring polystyrene. So all it is it's a system of rings instead of a system of linear chains. Rings, it turns out, don't entangle. They form these self-similar fractal structures that don't form an entanglement network, and this causes them to diffuse much faster. And so the Newtonian viscosity is much lower, like factor of 30 or so lower. However, if you look at the nonlinear response, you see this massive rise in viscosity in the rings when you apply an extensional flow. So the rings are becoming as viscous as the linear chains by going up factors of 20 or 30 in viscosity when you apply an extensional flow. And they wanted to understand what was driving this. And so the idea was, we were talking about it, and Michael Rubinstein said, well, you know, if you stretch out both a ring and a linear chain, they start to look a lot alike. A stretched out ring kind of looks like a stretched out linear chain. So maybe the rings are trying to behave like linear chains. So if you have a linear chain of length n and a ring of length 2n, then They're very different in equilibrium, but maybe when they stretch out, they act kind of the same. And so we can test that. And so we did. And so this is rate-dependent steady-state viscosities for linear chains. And so here's a linear chain of length 100. And if you try out a ring of length 200, they start to overlap in the strong flow regime. So you're like, hey, maybe this is a good idea. But if you go higher, you see that the rings very rapidly deviate from the linear chains. So there isn't some simple correspondence. It's not that simple. And so something else is emerging in the ring system that is causing the viscosity to rise faster and faster as you go to larger and larger chain lengths than is occurring in the rings, or than is occurring in the linear chains. And you can start to see that if you look at how the systems stretch out. So this is the distribution of chain end-end vectors for a linear system at different rates. And if I look at rings, all I want to point out to you here is look at the rings, particularly look at the rings at very low rates. What you see is the formation of this very long tail where most rings aren't changing at all, but a small number of rings at very low rates, rates too low to elongate rings, are becoming highly stretched. So you have this minority fraction of rings that just go crazy in extensional flow, even when the flow is supposed to be in the linear response regime. And I'll jump to what's going on.
So sorry to interrupt, but maybe just a couple of minutes.
Yep, I'm wrapping up. So this is the punchline. If you look at the system, so here's that experiment. Here's the simulations. And again, we reproduce what the experiments see. But if you look at the system, these stretches are being produced by this small fraction, you can see them visibly in the system, of rings that are just stretching out like crazy. Because what's happening is the fact that the rings are closed objects allows them to link together and form daisy chains like the ones I'm showing you right here. So what the rings are doing is they don't want to elongate, but every now and then a couple of them interweave together spontaneously and become a larger object that would want to stretch out. And they can continue to grow like this and grow like this. So here's that happening in action right here. Here's 3 rings that were separated at the beginning of flow. They come together, they link up, and then the flow sees them as a 3-ring long object and violently elongates it. And this means that you have a rheology, I'll skip the details, that is dominated by a tiny fraction of the system. So even as you go to linear response, rings can always link up at some time scale into longer and longer objects until they're long enough that they will be driven out of equilibrium by an arbitrarily weak flow. So here at the lowest rate that we could get in simulations, 75% of the stress is given by less than 1% of the system that form these very long daisy chains of supramolecular objects. And so this means that this is a system that can't be described with traditional polymer hydrodynamics. You can't use an average order parameter to describe its physics. And it's not an active system. It's a normal, statistical mechanics controlled system that has outliers that emerge in nonlinear flow environments to control its thermodynamics in a way that can't be described by typical theories. And so that's the punchline. There's some really cool work by Tom McLeish and Charlie Schaefer showing a similar phenomenon in associating polymers that we're looking at. So you should check that out. But this doesn't seem to be unique. This outlier-driven rheology seems to be a kind of a robust and interesting new regime that's going to challenge how we design models of polymer dynamics. So here's my collaborators. I'd like to acknowledge all of them, and then I'll just take your questions. So thanks.
Okay, thank you very much. So there is a question in the chat. So from Davide.
Hey, hi, Tom. Thanks for the very nice talk. So one question. So 2 questions. One. So don't you expect? So because of this topology, because of this kind of pseudo-linked topology, wouldn't you expect more than linear behavior? So the viscosity, the jumping viscosity, wouldn't you expect more than the linear behavior?
Yeah, exactly. And that's why it scales faster than the linear. I was kind of being narrative because we didn't reveal the answer till the end of the talk. But yeah, we originally thought it should be linear. We saw it was more than linear, and the reason it's more than linear is that rings self-assemble.
But the jump is more than linear, but then the absolute value of the viscosity is about the same of that the linear chain.
Right, linear chains of twice the size.
Twice the size.
We found that's just was a coincidence of their system. That's polystyrene at that molecular weight. Just so happens that the rings in the linear got to the same.
Okay.
They didn't like that it was a coincidence, but it was a coincidence.
Okay. And a technical point, how do you measure viscosity in your simulations when you
take the stress and you divide it by the strain rate?
But at every time point after that you start, so you take the stress, but you need to average it over.
Correct. So right, you can instantaneously calculate the virial stress in the simulation. You usually do want to average that over some time window. So like these are all time smoothed curves in the colors right here. Okay, so you take a window and you average over that window, and then you divide by the rate at that point. Okay, fine. Okay. Yes.
Thank you.
Yeah, are there any other questions? So maybe I can quickly ask. So is there what are the things which control the level to which these rings are threaded or entangled? Can you control that?
We're still trying to unpack that. So we have data for different molecular weights that we're exploring now in terms of but it appears, what we do know is that there appears to be, so this is the fraction of rings participating in links as a function of strain rate. So what we know is it becomes quite small at low Weisenberg numbers because the rings at lower and lower Weisenberg numbers have to form longer and longer daisy chains before they'll stretch out and form these objects. But once these objects form, they're stable because the flow stabilizes them. You can't unlink them while they're actively being pulled because the rings have to go all the way back through each other. And then there seems to be some saturation in this value that we believe is caused by runaway linking, but then eventually these supramolecules run into each other and they form sort of like a interpenetrating, percolating mesh of elongated supramolecules hitting other supramolecules. And then there's clearly an induction time, a time scale on which they can explore conformations that create new links, because if you go fast enough, you kill off the effect again. So but that's all we really know at this point.
Okay, thanks. So I think maybe there's time just for one very quick question from Jan.
Yeah, just a very quick question. How do you know that you have already reached the steady state because of all these effects that you just mentioned?
You don't. One of our conclusions is there is no such thing as a steady state in a ring polymer melt. Even at low Weisenberg numbers, like look at this blue system. This is our lowest rate system. It spent 30 longest relaxation times in the Newtonian plateau and then spontaneously formed links and started to have runaway thickening. And that is at a strain of 12, which an experiment could never, ever hope to get to, because that's a stretch of e to the 12, right? So the point is, experiments are never measuring steady states. Experiments are measuring some plateau region or some failure region associated with the setup. And that's why, you know, if anything, these little hash marks are me picking out points where the experiment failed, because that's the only meaningful way to compare. Because we have no shared steady state to get to anymore. We just have to say this system for this much strain at this strain rate. And we can't do better than that.